So Petra spoke about drones for many different applications. I will focus on one. I will talk about using drones for mapping. In this context, what's a map? Well, it's a precise measurement of things on the ground. And what things are we interested in? Well, it's the ground itself, undulations in the ground, the topography of the ground, things on the ground, roads, lakes. In many applications, we're also interested in buildings, if there are buildings on the ground. This kind of mapping has traditionally been done, it is traditionally being done using conventional aircraft, flying at high altitude, 1,000 meters and higher, covering areas of thousands of square kilometers. And we have an expensive aircraft, an expensive camera, high quality optics, and in the example image here, it's an aerial photo taken over the city of Strasbourg in France. And this example, 2,000 meters flying height, and with that camera, the size on the ground of each pixel is about 10 centimeters square. So that's the resolving power of, or ground sample distance as it's called, resolving power of in that application on that height. If we are only interested in smaller areas, let's say some 100 meters square, some hectares, then we can use drones for this. And then we could fly at 100 meters or even lower. We use cheaper drones, cheaper cameras. And in the example drone you saw there was at 120 meters, that camera produced a ground sample distance of a pixel size of 3 centimeters square. So it's actually better than what you get with the conventional technique over a smaller area, but still better. So a project, a mapping project with a drone is typically 4 phases. You have the planning phase, you take the images, you process the images, and then you study the output. And planning is quite simple. You have a map on screen, and you indicate the region where you want to fly. The software computes the optimal flying path, typically in a zigzag pattern, like this. And then you upload the flight plan to the drone flies and takes the images by itself, and then comes back and lands. And in the illustration at the bottom there you have these 3 so-called strips of cameras, where the cameras were when the images were taken, and the images are typically taken looking straight down. So now we have the images, and now comes the math magic. So the computer looks in the images, tries to find patches in the images that look the same. And in the illustration, there are 6 patches that I think it's the painting on the roof that is damaged, and the software found this in 6 different images, and then those coordinates of those patches are used together with the approximate positions of where the cameras were. And effectively, a ray is projected from the measurement inside the camera through the lens and downwards. And that's done from all 6 cameras, and you get a bundle of rays. And at the approximate intersection point of those rays, you get an estimate of the coordinates of that point, of that object point. And that process is repeated then massively over all the images and generating thousands of points. The final step, when this is then done for all, as I said, all the images, all the points, we get lots and lots and lots and lots of bundles of rays. And in the final process, it's called bundle adjustment because all these bundles of rays are adjusted simultaneously. It's an optimization problem. And the result of that optimization problem is that we get an estimate of the camera positions in space, the camera orientation in space, that may or may not be interesting, depending on the application, but also the coordinates of all the object points. That's typically what's of interest. But perhaps even more interesting is, or as interesting, is that you don't just get an estimate of the point, but you also get an estimate of the quality of the coordinate. How imprecise it is. Do we have a precise measurement with a small region of uncertainty, or is there some larger region of uncertainty? If we have coordinates from GPS coordinates from where the images were, when the images were taken, that can be combined with the image measurements to get more precise results. Also, if we have made measurements of points on the ground, so-called ground control points, that can also add precision, improve the quality of the result. As an example, I have a small data set here that's 250 images over the campus area at Umeå University. About 300,000 3D points from about 1 million measurements. And if I took that data, when I took that data set and put it into my desktop, it's like 3-5 years old. Decent graphics card. It took a few minutes to get the first results. If I want to get final results, it may take several hours still. So it's a computationally intense, it may be a computationally intense process. So, what results do we get? Well, typically 3 kinds of results. One is called a point cloud, and that's just lots and lots of points. And you see here at the top there's something called a sparse point cloud. That sort of forms the skeleton of the reconstruction. And every point there contains information, not just the coordinate, but also the uncertainty. It's about 300,000 in this example. It's possible to densify that point cloud with other algorithms, and below at the bottom you see a dense point cloud with over 30 million points. And in some applications this is enough. This is the output you need. Other applications, you want to visualize this together with other models of nearby buildings or things like that. But the third output, and the one that is perhaps the most important, are the maps. And what you briefly saw there, the color-coded image is a map. It means that every pixel value has a corresponding height, a height value. And this map can be processed further to, well, if you look at the image, you can see that you have blue there is low and red is high, so you can see the buildings stand out over the terrain. In some areas to the right, you can perhaps see some details in the terrain. And you can process this further to extract the buildings, if that's what you're interested in, or perhaps just keep the terrain. A sibling to that map, the digital elevation model, or DEM as it's called, is the orthophoto, which is a synthetic image generated from all images that we took. And it's a combination of all of them, and the combination is such that the distortions that are present in photographs are corrected for. So we have a photo that has one very important property. It's geometrically correct. Straight lines are straight. And we can measure distances, we can measure angles in this photo, and they correspond to reality. So that was in a few steps how the process looks like. So what's the output then? Well, what can we use the output for? And some applications here, for instance, if you have a construction site where you want to put a building, you have a permit. So, and the building should be placed at a certain place inside the property. So then you can do measurement, you put the formwork there, but before you pour the concrete in the formwork, then you probably want to know that you put the formwork in the right place, that the building will appear in the right place. Then when the building is built, you you want to know, or the authorities want to know, where did you put the building? Is it where it's supposed to be? If it's not, and surprisingly many buildings are not placed exactly where they should be. So that's one application. Another one is if you have, let's say you have a pulp mill that use wood chips for the process to create pulp. Then the wood chips are typically stored in piles. So then you want to know how much volume do you have? What's your inventory? So you can measure volumes. Or if you have, let's say, a construction site, early in the construction phase, okay, how much material do I have to remove to make that area become flat? And is there somewhere a hole nearby where I can put that material? If I do multiple flights over the same area, then I can track differences. Let's say I have a quarry, and how many cubic meters of gravel have been removed. You can use drones if you want to map details of cultural heritage. And this example is from a church in Strasbourg, in France. And in this case, the drone was flown not parallel to the ground, but parallel in front of the facade of the church. Or as a pitch to our final speaker, final keynote, if you're with the fire brigade and you arrive at the scene of a fire, you release a drone, it flies, you take the images, construct a DEM, then perhaps you can use that to figure out what roads can you use, where do you have free access, and what roads are blocked by fallen trees. So that was some applications of using drones for mapping, and some a glimpse of the theory, the math, the magic that's behind that makes it all possible. Thank you.
Thank you so much, Niclas. That was really, really interesting. And I mean, I'm not a developer, neither a mathematician, but still I got it all, I would say. But I have a question to you. What would you say is the biggest misconception about mapping?
I think it's that I mean, if you have these computer models, it's easy to be enamored, be convinced by a nice-looking graphic computer model that you can rotate and twist and zoom into and so on. Compared to a map, which is comparatively boring. It's just 2D and you can do measurements. But if you end up in a situation when someone tries to sell you something using a computer graphics model only, then you should ask them, what's the precision here? If I want to do something physically in the real world, interact with it, how precise is it? That's something it's easy to be, well, as I said, enamored by the beauty of computer graphics.
Yeah, that's interesting, really. And time is clicking. Time is going. You will go into the chat room now.
Yes, I will.
Yes, answer the questions from you. Thank you so much for joining us, Niclas.